I'm Norman Wildberger. Today we're going to look at the orthocenter of a triangle in hyperbolic geometry in the universal setting. This is a point of departure from this course and all the other courses that are currently taught in traditional hyperbolic geometry. In those other courses, the orthocenter doesn't in general exist. And so triangle geometry never gets very far off the ground. It's a big difference between that and what we're doing here. Here the orthocenter does exist, and it becomes a core pillar on which we build hyperbolic triangle geometry. So we're going to start out today by also introducing some very basic fundamental definitions that we're going to be carrying on throughout this course. So I'm going to tell you what a side is, what a vertex is, what a triangle is. We're going to define altitudes. Then we're going to talk about this orthocenter, which is where the three altitudes of a triangle meet. There are some other then related constructions which are also important. The ortholine, the orthostar, the ortho-axis. In particular, this ortho-axis that we'll end up defining turns out to be, in my opinion, probably the most important line in hyperbolic triangle geometry, and it has no parallel, as far as I know, in Euclidean geometry. So it's something completely new. Alright, so here is our basic two-dimensional representation of our hyperbolic geometry. We have a distinguished circle, which we'll call the null circle, and we have points like A1 and A2, and lines like L1 and L2. Okay, so here are some very basic definitions that we do need to peg down to make sure that we really are using language consistently and coherently. A side. A side, A1, A2 with a bar over it, is a set of 2 points. So for example, the set consisting of this point and this point together, that's a side. And this notation here is just a shorthand for the set A1, A2. And I remind you that when we're talking about sets, the order of the elements doesn't matter. So it's also the same as the set A2, A1. Dual to that is the definition of a vertex. A vertex, L1, L2 with a bar over it, is a set of 2 lines. And the vertex L1, L2 with a bar over it is just a shorthand for the set consisting of L1, L2. So there, for example, that would be a vertex, that pair of 2 lines thought of as a set. Now usually we think of a vertex perhaps as some kind of corner. In traditional geometry you might say, well, the vertex formed by those 2 lines, but it's not entirely clear what that word actually means. Here we're spelling it out very clearly. The vertex, which we're thinking about as being perhaps that point, but not necessarily, is just the pair of lines. That's our definition of it. Very important, these 2 definitions. One more elementary thing that we can do with a couple of points and lines is we can just take a single point and a single line and put them together in a set. And that will also be a useful concept, and we'll call that a couple. That's not a word that's used ordinarily in Euclidean geometry, but we're going to find it useful here. So a couple, denoted AL with a bar over it, is a set consisting of a point A and a line L. Okay, so AL bar over, that couple is just shorthand for the set consisting of the point A and the line L. Now we won't make any distinction at this point between couples where A lies on L or where A doesn't lie on L. So A might lie on L or it might not. We don't care. Alright, now a very fundamental definition. What is a triangle? What is a triangle in hyperbolic geometry? Or in fact the same definition really works in Euclidean geometry too. This is a term that's often not defined in Euclidean geometry. And so there's often a bit of ambiguity as to what it exactly means. We can all recognize the shape of a triangle, but what is it exactly? So here's our definition of what a triangle is. A triangle A1, A2, A3 with a bar over it is a set of three non-collinear points. So it's a set. And inside the set are 3 points, hyperbolic points. And all what we require is that those 3 points are not all on a line. They're not collinear. That would be kind of a degenerate case. But we'll exclude that. So a triangle is by definition non-collinear set of points. Now we always want kind of a dual object to all the definitions we're defining. So here's the dual notion, which is a trilateral. A trilateral, L1, L2, L3 with a bar over it, is a set of 3 non-concurrent lines. So it's just representing the set L1, L2, L3, where our 3 lines are completely arbitrary, except that they're not allowed to all go through the same point. Any 2 lines always meet in a point, but we don't want all of our 3 lines to meet in a point. So triangle, trilateral, they are of course very close, but they are different notions. So suppose we have a triangle A1, A2, A3. And perhaps in the plane it has points A1, A2, A3 like this. Now when we draw that triangle, we'll probably usually also draw the lines joining the 3 points. And sometimes I will draw the interior of that triangle to make it a little bit more visible, especially in Geometer's sketchpad. But in fact, the interior of a triangle is not really a well-defined notion in general in hyperbolic geometry. So we're in fact not going to define what we mean by the interior, and that shouldn't be a main concept for us. It's only a visual tool that we will use so that you can see the triangle if there's a lot of other stuff floating around as well. But this triangle A1, A2, A3 has a number of secondary objects associated with it. And here we have listed some of the most important ones. So first of all, the points of the triangle are by definition just A1, A2, A3. So we say this triangle has points A1, A2, and A3. So there are only 3 points to a triangle. These points don't count, the points on the lines don't count, only these 3 points in the triangle. It also has lines A1, A2, A1, A3, and A2, A3. So we call this a line of the triangle. Sides A1, A2, A1, A3, A2, A3. What is a side? Well, a side is just a pair of points. So that's a pair of points forming a set. That's a pair of points forming a set. That's a pair of points forming a set. Those are the sides associated to the triangle. It also has 3 vertices, namely A1, A2, A1, A3 bar. What does that mean? Well, a vertex is a pair of lines in a set. So this line together with this line forming a set, that's a vertex. And in our minds we will sort of think of it as perhaps being associated to that point there, but it's different from the point. The vertex is the pair of lines, while the point is just the point itself. So we're being a little bit fussy about language here. I hope you appreciate that. It's good to be fussy about language in mathematics. Okay, so we have 3 vertices. This pair of lines, this pair of lines, and this pair of lines. And there they are right there. Now we can make similar definitions for a trilateral. If we started off with 3 lines, perhaps these 3 lines, then we could also associate to it points, sides, and vertices. Okay, so I'll leave that to you to think about. We're mostly going to focus on triangles, and I don't always want to be saying the dual things of everything that I say, because then I'll be saying too much. So here's another definition. We'll say that a triangle A1, A2, A3 is dual precisely when one of its points is dual to the opposite line. What do I mean by opposite line? So we'll say that this line of the triangle is opposite to that point. And this line is opposite to that point. And this line is opposite to that point. Now the triangle is dual precisely when one of its points, at least one of its points, is dual to the opposite line. So in this case here, you see this point here is actually the dual point of this line. You can kind of see that because the tangents meet there. This is a special kind of triangle that we want to give a name to. We'll call it a dual triangle. Most triangles are not dual. A related definition is the idea of a couple being dual. We'll say that a couple, AL, is dual precisely when the dual of A is L. In other words, when the point and the line are themselves dual. All right, and here is the altitude line theorem. For any non-dual couple AL, there is a unique line N passing through A and perpendicular to L. So here is a point A, here is a point L. They are not dual because in fact the dual of L is this point L perp. And we're saying that there's a unique line N, which in this case happens to be this one right here, which passes through A and has the property that is also perpendicular to L. All right, what's the proof? Well, any line N which is perpendicular to L must pass through the dual of L. Because remember, that's how we define perpendicularity of lines. We said that a line N is perpendicular to L precisely when N passes through the dual of L. Now, since A is not equal to the dual of L, this point and this point are distinct because we're assuming the couple is non-dual. There is only one line through both A and L perp. That's the line that we usually write A, L perp. And so that's the line that we're looking for. It has the properties that it passes through A and is perpendicular to L. And we'll call that the altitude line to L through A. Or just the altitude, if it's clear what we're talking about. So if we just say altitude, we mean altitude line. Now the altitude line theorem that we just explained has a dual result, which is less intuitive to us. It's less familiar to us. So we have to think a little bit harder about it, even though officially it's exactly dual. It's the altitude point theorem, which says that for any non-dual couple AL, there is a unique point N which lies on L and is perpendicular to the point A. So here's the same picture. There's the point A, there's our line L, there was L perp before, there was that normal or altitude that we constructed in the previous theorem. Now we're claiming that there is a point lying on L which happens to be perpendicular to A, namely that point little n right there. This is exactly dual to the previous theorem. Okay? And the idea is that this point N is characterized by, first of all, lying on L, and it's also got to lie on the dual line of A, because that's what perpendicularity means in terms of points in the hyperbolic setting. So it's really the meet of A perp with L. There it is there. And we'll say that this point N is the altitude point to A on L. So here are two little exercises for you. Show that if you have any 2 points A and B, that the dual of the meet AB is the meet of A perp, B perp. And similarly for lines, so find the dual formulation of that. And in a second exercise, show that the altitude point that we've constructed here is the dual of the altitude line that we constructed in the previous theorem. So as this picture suggests, the line capital N and the point little n are dual to each other. Excellent. So now we come to our first major theorem. This is a theorem which is not obvious, and it's going to require some work to establish it. It is the Orthocenter theorem, which says that the three altitudes of a non-dual triangle are concurrent. What does it mean? Well, here's a triangle A1, A2, A3. It has three altitudes. What does that mean? Well, there's an altitude line from every point to the opposite line. So there is one altitude line from A1 to the opposite line. Another altitude line, or not just simply altitude, from A2 to the opposite line. It's this one right here. And altitude from A3 to the opposite line, it's this one right here. And the claim is that those three altitudes are always concurrent. And we're going to call that point H. So the meet H of the altitudes is the orthocenter of a triangle, denoted by H. That's the theorem we want to establish. Now that's an obvious analog of a well-known theorem in Euclidean geometry. And in Euclidean geometry, this theorem has an interesting history. It goes back to the ancient Greeks, but it was actually a favorite of many people. So Gauss established a proof of it. It turns out this theorem is not so easy to prove, even in Euclidean geometry. It's quite different from the meet of the perpendicular bisectors giving you the circumcenter, quite different from the meet of the angle bisectors giving you the incenter, or the meet of the medians giving you the centroid of a triangle. It's a little bit more complicated to establish this. And I understand that Einstein really liked this theorem. It was one of his favorite theorems in geometry. So we're going to establish it now in this hyperbolic setting. And as I said before, it's not a theorem in traditional classical hyperbolic geometry, which is a major failing of that subject. And here let me show you some examples of how it fails in the hyperbolic setting, in the traditional setting of the Poincaré disk. So have a look at these examples. If you've done some Euclidean geometry, you will know that often we have to be a little bit ingenious to find proofs in Euclidean geometry. We have to make very special constructions. We have to have insight to know what exactly we should be doing at a certain point. Insight is good, cleverness is good, but I sort of have this orientation that I would like to minimize the amount of cleverness required to do geometry. In some sense, I'm not really interested in clever proofs. I'm more interested in establishing a technology that allows anybody to prove theorems. So to me, proving theorems is something that's necessary, but should be relatively straightforward once you've established the groundwork properly. And you're going to see a little bit of it here in this theorem here. I'm not going to give you anything particularly clever. We're just going to do the obvious thing, and we're going to make a computation. And we're not going to shy away from the computation just because it's a little bit involved. That's going to be our basic attitude towards proving things in hyperbolic geometry. Let's just compute something. Let's not think for 2 weeks about the clever thing to do. Let's just do the obvious thing, even if it takes a couple of hours. Okay, so what are we going to do? We're going to establish coordinates. We're just going to compute everything. So the point A1, we'll assume it's the point with homogeneous coordinates x1 to y1 to z1. A2, the point x2 to y2 to z2, and A3, the point x3 to y3 to z3. Now we're going to establish what are the equations, or the forms of those altitudes. And then we're going to try to see that those three altitudes are concurrent. Alright, let's have a look at the line joining A2 and A3. That's given by the join of points theorem. We know exactly that the j function applied to these three numbers here gives us the three coordinates of the line A2, A3. So there it is right there. Each of those is like a little 2x2 determinant. Okay, and so now what the altitude is, the first altitude from A1, which is perpendicular to this thing here. How are we going to get that altitude? Well, we know what an altitude is from the altitude theorem. It's a line that joins the point A1 to the dual of that line there. Okay. The dual of this line is just exactly the same thing with square brackets instead of round brackets. So what we really need to do is we need to take the join of this point here and this point here regarded with square brackets. And that's again exactly a join operation with the j function. Let's do it. So it's y1 times this quantity here minus z1 times this quantity here. That's the first coordinate. The second coordinate, which is down in this next line, is z1 times this quantity minus x1 times this quantity. And the third coordinate is y1 times this quantity minus x1 times this quantity. And that's the first altitude. And then there's going to be a similar formula for the second altitude and a similar formula for the third altitude. And we don't really need to do those separately because we can just rotate indices. Because we have these indices 1, 2, and 3 representing our 3 points, if we want to get n2, it's just going to be the meet of A2 with A3, A1. So what we do is we just rotate each one of these indices. 1 goes to 2, 2 goes to 3, and 3 goes to 1. Okay, so we're going to have then a big determinant, but it's a little bit painful to write down. And so we're going to introduce a little bit of notation to make it easier to write down the determinant that we need to compute. Here's what we're going to do. So let's have a look at the first term that appears here. It's y1, x3, y2. We know that that term has one variable with an index 1, one variable with an index 2, and one variable with an index 3. So y1, y2, x3. And we know that that's true of all the terms that appear here. For example, that term chosen randomly, one thing with an index 1, one thing with an index 2, and one thing with an index 3. Now that means that we can take a term like this, say y1, x3, y2, rewrite it with the indices going up, 1, 2, and 3 in that order. And then once we've done that, we can drop the indices because we know that the first one's index 1, and the second one's index 2, and the third one's index 3. So this is a little bit of sort of suspect notation perhaps. We're throwing stuff away that we don't really need, just temporarily to make our computation easier. Instead of writing y1, y2, x3, I'm just going to write y, y, x. And it's easy to go from here to here because we'll just put the index 1 there, the index 2 beside this one, and the index 3 beside this one. Alright, so now I'm going to rewrite this thing here in a more compact form without the indices. So this first one is y1, y2, x3, that's just y, y, x. The next one, minus y1, x2, y3, that's minus y, x, y. Minus z, z, x, and plus z, x, z. So I've rewritten that just with those 4 terms. And then the same thing here is written there, and the same thing here is written there. I'm going to expand this in a second so you'll have a better look at it. But then what do we do to get the second and the third rows is we just rotate the indices. What does that mean? Well, it just means we take something like this term here, y(x), and move the x from the last position to the first position. So that instead of having index 3, it now has index 1. And the y moves from the first position to the second, and this y moves from the second position to the third. So we just take each one of these terms and rotate each one of them. The x goes to the front and the other ones move forward. The y goes to the front, the other ones move forward. The x goes to the front, the two z's move forward. The z goes to the front and the other two move forward. So to go from here to here, just rotate. And that's how we go from the first line to the second, and then from the second line to the third. Let me show you a little bit more close-up of this thing here so you can see it more clearly. So to prove that these three lines now are concurrent, we need to prove that the determinant of this 3 by 3 matrix is 0. Well, that sounds like an onerous job, doesn't it? Because the determinant is actually some of these 6 terms. This times this times this, minus this times this times this, and so on. It seems like it's going to be a lot of work. But there is a simple observation that makes it all very easy. The observation is that if we add these 3 rows together as a vector, we get the vector 0, 0, 0. In other words, this term plus this term plus this term is 0. Everything cancels. Let me show you that. So y(x), where can we find that y(x) again? Right there it is with a minus sign. yxy, it's got a minus sign there, it's got a plus sign there. zzx with a minus sign there, a plus sign there. zxz, a plus sign there, and a minus sign right there. xyy, plus there, minus there. We've already talked about this one. We've already talked about this one. No, we haven't. Minus xzz there, plus xzz there. We've already talked about this one that came from there. So all of those terms cancel pairwise. One's positive, one's negative, total of 0. Same thing here. This plus this equals 0. You can check it. And this plus this equals 0. That means the 3 rows sum to 0. In other words, they're linearly dependent. And that forces the determinant to be 0. If you know a little bit about linear algebra, you'll know that a determinant signifies a volume of sort of a parallelepiped formed by the 3 vectors. And if the 3 vectors are summing to 0, it means that they're all lying in a plane. And so the parallelepiped formed by them has volume 0. So that's an easy, admittedly clever, way of seeing that the determinant is 0. And if the determinant is 0, it's telling us that the 3 altitude lines always meet. So that's proof of our first main theorem. Please give it some thought. Later on, we're going to see that what's going on here can be interpreted in another way. It's actually a remarkable connection between this and something called the Jacobi identity in linear algebra. But I'll tell you about that a little bit later. Right now, just think of it as a computation. We've made this computation, and now, no matter where the 3 points are, they don't have to be inside, they don't have to be outside, they can be anywhere they want to be. In other words, as long as we start with a non-dual triangle, so that the altitudes actually are well defined, then the 3 altitudes are meeting, they're concurrent. The orthocenter theorem also has a dual result. The ortholine theorem. This is not really a result in traditional hyperbolic geometry. It says that the 3 altitude points of a non-dual triangle are collinear. So here's a picture A1, A2, A3. There's a triangle. The three altitude points, they're the points that lie on a line which are perpendicular to the opposite point. So the dual of A1 is something like this. So there's one altitude point. The dual of A2 is this. There's another altitude point. The dual of A3 is this. There's the other altitude point. And we're saying that these three altitude points are collinear. And the join of these altitude points is called the ortholine of the triangle. We denote it by capital H. That's the ortholine of the triangle. That's exactly dual to the orthocenter theorem. So in other words, the proof that we wrote down can be completely rewritten, word for word, exactly the same, just where we dualize everything. So probably a good exercise to write out a proof, or at least write out enough of the proof so you're convinced of that. Another exercise, show that this orthocenter that we defined earlier, H, which is up here, and this ortholine, capital H, are in fact dual. The orthocenter, the ortholine, they are dual to each other. Here now are some examples of geometry sketchpad diagrams with accurate illustrations of orthocenters and ortholines for various triangles. Now we need to introduce one of the other great theorems of projective geometry, going back to the founder of the subject, Gerard Desargues, who in the 17th century proved the following result: that in the projective plane, if two triangles A1, A2, A3 and B1, B2, B3 are perspective from a point, there they are, there's A1, A2, A3, and there's B1, B2, B3, then they are perspective from a line. They're perspective from this line here. So let me explain what does that mean. So to be perspective from the point means that if you look at them from the point here, then A1 and B1 line up so that these 3 points are collinear. A2 and B2 line up, so these 3 points are collinear, and A3, B3 line up, so these 3 points are also collinear. So if that's the case, then the two triangles are perspective from a line. And what does that mean? Well, it means that if you join A1, A2, and you join B1, B2, then those two lines meet at a certain point. And if you look at A1, A3 and B1, B3, those two lines also meet at some point. And if you look at A2, A3 and B2, B3, these two lines also meet at a point. And the claim is that these 3 points are collinear. Desargues' theorem, one of the foundational theorems of projective geometry. And we're now going to use this theorem to establish something very important. So this is actually the first time that I'm going to actually use a result of projective geometry in our sort of setting for hyperbolic geometry here, our formal, official setting. So it means that I really owe you a proof of this. So at some point I should go back and prove this theorem. But for now, let's assume this theorem is true and let's use it in an interesting way. So purely in the framework of projective geometry, we're now going to use Desargues' theorem to establish the polar of a point with respect to a triangle. So we are going to start with the triangle A1, A2, A3. There it is right there. And we're going to have an auxiliary point P, which is variable. This point P could be anywhere. Now associated to the point P, we can first of all draw Cevian lines. Those are the lines that go through P and the points of the triangle. So A1P, join that, that's one Cevian. A2P, join them, that's another Cevian. And A3P, that's another Cevian. So these are the three Cevians in blue, here, here, and here. And those Cevians meet the opposite lines in three additional points. So A1P meets the opposite line in a new point B1. A2P meets the opposite line here in a new point B2. And A3P meets the opposite line in a new point B3. So given the triangle A1, A2, A3, to any point P, we can draw these Cevians and we get this new triangle B1, B2, B3, which is perspective to the original triangle via the point P. This is exactly a situation where we can apply Desargues. Because if we're looking at the two triangles from P, then necessarily A1 and B1 line up, A2 and B2 line up, in other words they're on the same line, and A3 and B3 line up. So, Desargues' theorem tells us that these two triangles, A1, A2, A3, and B1, B2, B3, must be perspective from a line. What does that mean? Well, that means that if you look at corresponding lines of those two triangles, then they meet in 3 points which are collinear. So let's see if we can find them. So let's look at A1, A2. That's one line of one of the triangles. And the corresponding line B1, B2, it's that line there. And these two lines meet at that point. And how about A2, A3? There's A2, A3 and meets B2, B3. Okay, well, it'll be some point up in that direction there, off the page. And A1, A3 meets B1, B3, which is right here, in this point. And Desargues' theorem tells us that these three intersection points, this one, and the one that's up in that direction, they are necessarily collinear, forming a line that we might call L. So we can think about this now in this way. We can think that if we start with this triangle A1, A2, A3, and we fix that triangle, then for every point P, there's an associated line L. And this line L is called the polar of the point P with respect to the triangle A1, A2, A3. It's a different use of the word polar from Apollonius's use. It's a little bit, it's not quite as nice as Apollonius's notion of polar, but it's still quite useful in triangle geometry. Sometimes if we want to make it clear that we're talking about this kind of polarity, we'll talk about the Desargues polar of the point P, reminding us that it's really Desargues' theorem that's responsible for it. And here's the notation that I'm going to use. I'm going to say that the line L is P with a hat on it. That's going to mean the Desargues polar of the point P. So given a point P, we can find its Desargues polar P hat, which is a line, with respect to the fixed triangle A1, A2, A3. Now we can do this for any point P, and now going back to our hyperbolic geometry, we think, well, we've just established the existence of this interesting point, the orthocenter. So one thing we could do is we could find the Desargues polar of that orthocenter. And that turns out to be an interesting thing to do. We're now going to define some very important points and lines associated to a triangle in the hyperbolic setting. We're going to define the Orthic axis, the orthostar, and the ortho-axis of a triangle. We're going to work with this fixed triangle A1, A2, A3. There it is there, A1, A2, A3. And we're going to assume it's a non-dual triangle, so that the altitudes are well defined. There they are in blue. And those three altitudes meet in the orthocenter H. Now from that orthocenter H, we're going to construct the Orthic axis, which is the Desargues polar of H with respect to the triangle A1, A2, A3. I remind you how you get that. So we look at where the altitudes, which are the Cevians in this case, meet the sides of the triangle, And then we connect them and see where this one here meets this line there, where this one here meets this line, and where this one here meets this line. Then these 3 points are collinear by Desargues' theorem, and that's the polar of the point H. We're going to call that polar the orthic axis. That's standard terminology in Euclidean geometry, where this is a standard construction. But now we can do something that we can't do in Euclidean geometry. We can take this orthic axis and we can define its dual point S. So this will be called capital S, that's our name for orthic axis, and its dual point, which will be out here somewhere, in this case constructed by tangents if you like, we're going to call that the orthostar of the triangle. So from the orthocenter to the orthic axis via the Desargues polarity, and then from the orthic axis to the orthostar via duality. And now the line joining H and S, this line here, that's going to be called the ortho-axis of the triangle. We'll denote it by A. And in my geometer's sketchpad pictures, this line will typically be orange, but here it's red. And its dual point, also of interest, will lie on the ortho line. We'll call it little a. Call that the ortho-axis point. This line, this axis, this ortho-axis A, is going to be very important for us. I claim that the ortho-axis A is the most important line in hyperbolic triangle geometry. We're going to see a lot of evidence for that as we carry on. So this is a very rich diagram. Already you can spend a lot of hours thinking about this and constructing some examples of all these things for yourself. So please do that. Get out your straight edge, draw a base circle, draw some random points A1, A2, A3, and construct all of these things. You can do it all with a straight edge. Of course, if you have geometer's sketchpad or circle and ruler or Cinderella or Cabri, you can do it just with a few clicks of the mouse. It's an excellent exercise. All right? So construct some orthocenters, some orthoaxes, some orthostars. Have a look what they look like. Here are some examples in geometer's sketchpad showing these various constructions. Next time, we are going to carry on thinking about consequences of understanding perpendicularity. So we're not yet approaching the metrical notions of quadrants and spread. We're going to stick with perpendicularity, and I'm going to show you some more beautiful theorems that result just from that notion. So more on perpendicularity next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.